talk, we have William Slofstra from IQC at the University of Waterloo. And William hopefully will decipher for us the algebraic side of the MIP star equals RE result. And the floor is yours.
Thanks, Andrea, and thanks to the organizers for keeping this going and for the opportunity to speak. So what I want to talk about is, well, first, the Kahn embedding problem. So if you've seen a statement for this, it's usually stated something like this. Does every separable finite von Neumann algebra embed in Ru, okay, and or sometimes called R omega, and omega or U is an ultrafilter, and R is the hyperfinite 2-1 factor, and Ru is the ultrapower of the hyperfinite 2-1 factor. And on the other hand, we have this recent theorem, so that MIP star equals Re, which now I'm sure everyone in the audience has heard, implies that the Kahn embedding problem is false. And looking at these two statements, the theorem that MIP star equals Re and the Kahn embedding problem, I'm not going to say what MIP star equals Re is, but we've been having some talks and we'll continue to have talks about it, I guess, so I can skip that. It probably seems like these are kind of two different worlds, and these problems really aren't connected at all. And part of the reason the Kahn embedding problem has become so famous is that it's not just a problem about embedding von Neumann algebras in this ultrapower, but it has many equivalent formulations. And so the corollary that Kahn embedding is false because MIP star equals Re uses an equivalence of the Kahn embedding problem with what's called Cyrilson's problem, which is really about the separation between quantum correlation sets. So what I want to talk about is kind of maybe how can we see if these two worlds of von Neumann algebras and non-local games are directly connected. So we'll see how successful this is. There is a way to see that these are directly connected, more than one way really, but we'll see if it fits into 50 minutes. Also, I don't like giving very technical talks, but I don't think it would be possible to do justice to this topic if unless I leave you with some idea at least of what Ru is. And to do that, we do need to get into some technicalities. So I apologize in advance. If it would make it easier to have the slides and follow along at kind of your leisure, moving backwards and forwards, you can download these slides at elliptic.space/slides/simons2020.pdf. So to start with, I know that we need to say what a von Neumann algebra is eventually, and I know that not everybody works with algebras. I can't explain the basics of algebras and the kind of basic concepts for them in this talk, but for people who have kind of seen them and but maybe don't work with them every day or haven't seen really worked with them in years, what I can do is try and jog your memory. So I'm just going to kind of quickly mention some basics just to see if that helps. So when we talk about an algebra, it's a very simple type of object. It's just a vector space with a bilinear multiplication. Usually, and definitely in this talk, we assume that algebras are associative. So it doesn't matter what order we do multiplication in. AB times C is the same as A times B times C. And also that algebras are unital. So there's an element which acts like an identity element with multiplication. Now, what are some examples of algebras? Well, there's the matrices, or if you want to be a little more sophisticated, you can take a Hilbert space and look at bounded linear operators on that Hilbert space. And actually, if you want, it would be perfectly fine for this talk. Every time I say algebra, just think matrices or B of H. And in fact, that's exactly the kind of spirit we should have for the subject we're studying, as we'll see. Now, just to think about these examples a little bit further, both of these have an additional operation, which is the conjugate transpose operation, or taking the adjoint. So this is called a star operation. It's an antilinear multiplication reversing operation. And an algebra with this type of operation in addition to its multiplication and linear structure, is called a star algebra. So in this talk, I'm just going to say algebra, and I'll basically always mean unital associative star algebra. Now, there's two more basic concepts I just want to try and jog your memory on. One is homomorphisms. Okay, so homomorphism is a linear function between two algebrans such that the operations of the algebra are preserved. And we have kind of three operations, if we're willing to think about the identity as an operation. Okay, so we have multiplication has to be preserved, the star operation has to be preserved, and the identity has to go to the identity. So for an example of an algebra homomorphism, one which we'll use later, we could think about taking n by n matrices and embedding them in nk by nk matrices just by taking x to x tensor with the identity. That's an example of an algebra homomorphism. Preserves multiplication, addition, and the star operation. And the identity goes to the identity. And finally, the last basic concept about algebras that we're going to be using all over the place is the idea of quotients. And so you don't need to kind of read through all these definitions. I'm just going to kind of point towards some things. So the idea behind quotients is that if we have a subspace of the algebra, which is kind of closed under multiplication, not just inside the subspace, but by all elements of the algebra. So if you've got something in the subspace, something in the algebra, then ax, xa, and also the star of x all stay inside this subspace. That's called the subspace is called an ideal of the algebra, and the quotient space is also an algebra with the kind of induced operation from the algebra A itself. And it's very nice to so ideals are really nice to work with because we don't really need to say necessarily everything that's in the ideal. Just like when we talk about a subspace, we can talk about the subspace spanned by a set. We can talk about the ideal generated by some set of elements in A. So that's just defined to be the smallest ideal actually containing those elements. Okay, and we can use this idea of taking the ideal generated by a set of elements and then taking a quotient to make lots of new algebras given an algebra A. Right, so in particular, if we just took some sequence of elements x1 up to xn and y1 up to yn, and we want a new algebra which is like the algebra A, but where xi is actually equal to yi, we could just take the ideal generated by x1 minus y1, x2 minus y2, and so on. And now, when we quotient out by this ideal, we're setting all these elements to 0. Okay, and so in this new algebra, all x1 will be equal to y1, x2 equal to y2, and so on. And so we get this new algebra. Unfortunately, unlike when we say take the span of a set of elements to get a subspace, taking an ideal, we don't have very good control over what ends up in the ideal because it has to end up being closed under multiplication. And so it's possible that even for a very small set of elements, x1 up to xn, the ideal generated by those elements could be the whole algebra itself, for instance, or very large at least. By the way, I think I didn't include the notation for the ideal generated by x1 up to xn. So we use just kind of round brackets. So this here is the ideal generated by the elements x1 minus y1 and so on. And if this ideal is equal to A, then of course this algebra would just be A mod A be 0. So there's no guarantee that the algebra we take when we do this, or that we get when we do this, will be interesting. It might just be trivial. Okay, so that's the part designed to jog your memory. And now I want to get into something which could be familiar, maybe not, and that is finally presented algebras. For me, this is where algebra gets kind of fun. Okay, so we start with another familiar algebra, which is polynomials in n variables. Right, so this is an algebra. We can multiply polynomials, we can add polynomials, we can multiply by a scalar. And there's no reason really that our polynomials have to have commutative variables. Normally, we think of polynomials as having commutative variables, but we could just define them in exactly the same way, but say that xi and xj is not necessarily the same thing as xj times xi. We get a much larger set, but really just kind of very easy to understand the elements of this set, just as it is to understand the algebra of polynomials. Now, this isn't a star algebra. So it's not an algebra, it's not a star algebra, but we can make a star algebra version just by formally adding in the stars of every variable. Okay, so the star algebra of generated by non-commutative variables x1 up to xn is just the polynomial, the non-commutative polynomial algebra generated by x1 up to xn and x1 star up to xn star. And the star operation does what you'd think. It takes xi to xi star, and it takes xi star to xi back again. And then we just extend that in such a way to make it anti-linear and multiplication reversing. Now, when we start with this star algebra of non-commutative polynomials, we can get a lot of new examples of algebras by taking quotients of this algebra. So if I just write down some f1 up to fm and g1 up to gm, I can take the ideal generated by f1 minus g1 up to fm minus gm, and then I can take the quotient of the polynomial algebra by this ideal. And we get an algebra which is denoted c star x1 up to xn. So these are the generators, and then kind of mod the relations f1 equals g1 up to fm equals gm should be there. And an algebra of this form is called a finitely presented algebra. Okay, so the choice of generators and polynomials is called a presentation, and it's finite because we've picked only finitely many variables and finitely many relations. Now, so a finitely presented algebra is an algebra of this form, and it's easy to write down examples, even pretty easy to start writing down interesting examples. So we don't need to go through all of these examples. I put them in here just to give you some idea that we can really kind of go nuts with this idea. This is just kind of the beginning. But let's just take the first one. For instance, if we want to talk about, maybe we want to have a variable which behaves like a unitary. So we start with c star u. U will be our single variable. That means we really have polynomials in two variables, u and u star. And then we mod out by relations which say that u star u and u star are equal to the identity. So what we get is an algebra where the elements are polynomials and u star. And whenever we see u star u or u star, we can cancel it out. So it behaves just like a unitary inside this algebra. And we can write down all kinds of things. For instance, if we want to talk about k outcome projective measurement, right? We can have variables p1 up to pk, write down relations that say that they're actually self-adjoint projections and that they're orthogonal, and then that they sum to the identity. Or if you like Clifford algebra, we could write down the algebra generated by generators, which are self-adjoint and square to the identity, and which anti-commute. And we can just kind of keep going with this. Any type of relation we have, we can write down an algebra for it. Now, although it's really fun to play with these kind of star algebras coming from quotients of polynomial algebras, I think even among algebraists, there's still a bias that the algebra we like the most is matrices. They're just kind of the first example we see where we have a non-commutative algebra. And so it would be really nice if we could just put everything in terms of matrices. And so if we have some algebra, what we can do is look for homomorphisms from the algebra to the matrices. And these are called representations of the algebra. So it's kind of a way of writing down for every element a matrix, such that when we multiply the matrices for different elements together, it would be like we multiplied the elements of the algebra together. And when we have a finitely presented algebra, there's an easy way to talk about homomorphisms to, well, to any algebra really. So if A is finitely presented, then a homomorphism to an algebra B is just a tuple of elements in B, such that when we plug these into the relations are satisfied. Okay, so let's just see an example of that. Let's look at representation of this algebra of a single projection, which is so a single variable P, self-adjoint, and squares to itself. And we're going to look at homomorphisms to B, which is the algebra of n by n matrices. Okay, so it's supposed to be an element of B for every generator. We have only one generator, so it's just an element P in matrices, such that the relations hold when we plug P into them. So we plug this matrix P into the relations, And we see that P has to satisfy the relations that P star equals P and that P squared equals P. So a homomorphism from A to B is just a self-adjoint projection in n by n matrices. And that's where where all these names come from. The algebra of a unitary, the representations of it are just unitaries. For the algebra of self-adjoint projection, we just saw that the representations are projections. And for the algebra of a k outcome projective measurement, the representations are k outcome projective measurements. So maybe this is a good time to pause just in case somebody wants to type in a question into the chat.
Hi, William, I have a question. So, so when you're taking this homomorphism, you're mapping the elements of A to projections, you're saying, right? But so A is like the algebra of polynomials. So do I understand correctly that you're mapping sort of polynomials in this algebra to basically polynomials in the projectors, essentially?
That's right. So when you take a general polynomial in P, then you would map it into the matrices by plugging in big P for little p. So you would get a polynomial in big P. And that works. That's how the recipe for any finitely presented algebra. We have some polynomial in x1 up to xn, and then we just plug in our b1 up to bk. Oh, k should be n here. That's important. Pardon me. So there's a bi for every xi. Yeah. Okay, so let's continue.
Can you always get an isomorphism there? Because this just says you get homomorphisms, but the
well, actually, great question, because that's half of that is my next slide. So that's exactly the question I think we should ask if we really think that well, we want to just represent everything in terms of matrices. The problem is, can we really see everything inside the algebra A in terms of matrices? This homomorphism could have a kernel, in which case we might be missing out on a lot of information from A inside the matrices. And so what we really want to know is, when do we have injective representations? When can we think of A as a subset of B? So I just put this down in case people haven't seen it before. If we have an injective homomorphism of A to B, we say that A embeds in B. So what we really want to know is what algebras A embed in the matrices. Special name for these are called matrix algebras. And it's pretty easy to see if you embed in the matrices. It's a finite dimensional vector space. So you'd have to be a finite dimensional vector space as well. And you can go backwards. So A is a matrix algebra if and only if A is finite dimensional. So not quite the same thing as being an isomorphism. The only things, so there's not many algebras that are isomorphic to the matrices that, let's say, not many finitely presented algebras. So the question then is every algebra a matrix algebra? And it's easy to find non-finite dimensional algebras. So I'll just skip back to my examples here. These last three examples actually all happen to be finite dimensional. They're kind of special in that regard. But this first one, this unitary, arbitrary powers of it don't have to vanish. So we could just talk about u1, u squared, u cubed, and so on. So this algebra is infinite dimensional. So it's not a matrix algebra. So thinking about this, we might think, well, it's nice that we could, it would be nice if we could think of all algebras as matrix algebras, and we would never have to think about anything except matrices. But clearly that's way too strong. We can't use matrices to understand algebras in general. But people were surprisingly resistant to give up this idea. And so they thought, well, maybe we should modify this. And this is where it actually helps to think as a computer scientist or physicist, I think. If we think kind of operationally, we can only work with finitely many elements of A at any given time. So let's modify the definition. We don't really care about whether the kernel is non-trivial in some specific representation. What we just care about is, for the given set of elements we're working with, are all of them separated by the representation. So an algebra A is said to be residually finite dimensional if for every finite subset of A, there is a homomorphism to the matrices such that phi x is not equal to phi I for all x and y in F, right? So it would be injective if it was for all x and not equal to y in A, but we just look at this finite subset F and ask that we separate pairs on that finite subset. And the idea is that you could be residually finite dimensional. The n might depend on what subset F you pick here. So the larger F you pick, or the kind of maybe the larger degree of polynomials that you pick in F, if this is a finitely presented algebra, maybe the larger n has to be to actually do the separation. But for any finite set, you can find some homomorphism like this. Unfortunately, this idea doesn't work either in the sense of could we use this to understand all algebras, since there are non-RFD algebras. So, but maybe we're not ready to give up, okay? And again, we should now think like physicists. Maybe we are willing to tolerate some noise in our representation. Maybe it doesn't matter if the multiplication is exact. So maybe when we multiply two matrices together, it's fine if it's just close to what it was supposed to be, okay? So we can define a notion of what's called an epsilon representation. It's easiest to define this for finitely presented algebras. So let's say we have a finitely presented algebra, and then an epsilon representation. Well, remember, a representation would be a tuple B1 up to Bn, such that Fi B1 up to Bn is equal to Gi B1 up to Bn. So now we'll say an epsilon representation is a tuple where the difference between these two matrices is small in some norm. So we can just pick our favorite norm for this definition. We get different notions of epsilon representation for different norms. But my favorite norm is this little Hilbert-Schmidt norm, so we'll pick that. Okay, so that's where we take the trace of A star A and then divide by the dimension of the space if we have an n by n matrix and take the square root. The point of this normalization, we could think about that as if we plug in the identity matrix in here, the trace of the identity is n. So then the little Hilbert-Schmidt norm gives us 1 for the norm of the identity. Any questions about the definition of, yeah, it is presentation dependent. Yes, the question is it presentation dependent? And it is, but what will happen is that if we only care about epsilon asymptotically, then if we change the presentation, there'll be epsilon representations of one presentation will correspond to O epsilon representations of another representation. Okay, so what we really need to do then is say, can we use epsilon representations to understand algebras in general? But we've been interrupted. We should talk about, like, does it really make sense to talk about these epsilon representations? And maybe a good way to answer that would be to see if they come up in any applications. It turns out they do come up in non-local games. Lucky for us, you know, something very connected to this, this workshop. How could that have happened? Okay, so I want to talk about a specific type of non-local game. So this comes from Helton, Meyer, Paulson, and Satriano. Okay, so so remember, with a non-local game, I'm going to, since I have to go through all this algebra stuff, I'm going to assume that you can get what a non-local game is from some of the other talks if you're not familiar with it. But it can be given by very simply in terms of input and output sets, which for simplicity I'll assume are the same for both players, and a winning predicate, which given the outputs and the inputs says whether the players win or lose. Usually we include a probability distribution on inputs here, but I only want to think about perfect strategies, and it doesn't really matter what the input distribution is, so I'm not going to worry about that. Now, the definition of Helton, Meyer, Paulson, and Satriano is that a non-local game is synchronous if whenever Alice and Bob receive the same inputs in this game, then they win, if and only if their outputs are the same. So if they get the same inputs, they have to output the same outputs, and if they do, they win. And for synchronous games, we can actually write down a special algebra. So it is the algebra generated by variables. So talk about star polynomials in these variables, mxa for x in inputs and a in the outputs. And we want these mxa's to be the projectors in a measurement that the players will do on input x. Okay, so the variables have to sum to 1 over a, and the variable should be projections. And also we put in this condition that if they lose on inputs x and y and outputs a and b, then we want the product of these projections mxa and myb to be 0. So here's this algebra, and it's a theorem that perfect finite dimensional strategies for the game correspond to finite dimensional representations of this algebra. So correspond here means you have to kind of mod out by, let's say, non-degenerate strategies. You don't want your strategy to have some block of the matrix outside of the support of the state. You have to get rid of all that stuff. But if you do, then you get a correspondence between strategies and representations. Now, how do epsilon representations enter into the picture here? Well, we might say, I think this would be the way to tackle it. What would happen if we were just to take one of these finite dimensional representations and modify it a little bit so it wasn't exactly a representation anymore, just an epsilon representation? And then we could trace through the construction of the finite dimensional strategy and find out that what we got was a strategy which was close to perfect. That should seem pretty intuitive. And actually, it turns out that there's a correspondence between epsilon representations of the algebra and perfect strategies for the game. This hasn't been written down anywhere that I'm aware of in exactly this quantitative form, but Thomas and I wrote it down for linear system games, and I think the same proof should go through. So I'll say this just say to be kind of safe that this statement is, formally speaking, a conjecture based on that result for linear system games. But it says that if we start with an epsilon representation, then we can get a kind of a poly epsilon perfect strategy for G, and vice versa. Given a close to perfect strategy for the game, we can turn it into an epsilon representation. Okay, so it's a good time for questions as well.
Yeah, since there's always a trivial representation, the 0, in the theorem, does it mean corresponds to finite dimensional non-trivial representations in some way?
Yes, I got a trick to get out of that. Oh, I'm hearing myself on your speakers. Where do we define homomorphism? Homomorphisms have to send the identity to the identity. So that rules out the 0 homomorphism. So there isn't always a trivial homomorphism. If you don't, if you take a slightly different set of definitions, then you have to come up with some other way to rule out the trivial representations. They don't give you a strategy, as you correctly guessed.
Okay, but they don't have to be some kind of faithful or whatever it's called, like injective.
Right, they don't have to be an embedding, just any representation at all. And that will be significant later on when we talk about this Kahn picture.
Okay.
Okay, so that was our interruption about non-local games. So hopefully it kind of illustrates that it is natural to think about epsilon representations of an algebra. So here was our definition again of what an epsilon representation was. Let's go into this question about whether we can, our kind of version of approximate, of residual. So we had finite dimensional and then residual finite dimensional. Then we should have, what does it mean to be captured by approximate representations? So I don't know a standard term for this, so I kind of just mashed together some terms that are from different special cases. So we'll say A is approximable by matrix algebras if for every finite subset of the algebra there is an epsilon representation of A, right, which is just given by a tuple, such that for every pair of elements, non-equal elements in F, they evaluate to different things on this tuple. Now, this is the idea of what we want to do, right? This would make sense. This kind of matches RFD-ness, that for every, so RFD would be for every finite subset, there's a representation such that this is true. But for technical reasons, we have to kind of modify this. There's a bunch of things in here that don't make sense. First one is, what should we set epsilon to? We don't have a natural cutoff to know what's interesting for epsilon. Well, we can get around that easily enough. Maybe we want to just say it's for every epsilon. So maybe the the dimension of this epsilon representation will have to grow based on the size of this finite subset and epsilon. As epsilon gets smaller and smaller, the dimension of the epsilon representation will grow. But there's a second problem, unfortunately, which is that, like, if we consider F1 and G1, they're supposed to be equal in the algebra, but all we're guaranteed is that these two things are close together in the epsilon representation. They're not necessarily equal. So it doesn't necessarily make sense to just plug in B1 to Bn into an element of the algebra. So what we have to do is actually take a finite subset of polynomials and then say that maybe these two are not equal if for all polynomials which give different elements in the algebra. If the polynomials give the same element of the algebra, then they'll be close based on the smaller epsilon is, the closer they'll get. Okay, so that wouldn't really kind of capture the right idea. So we want to do this for all polynomials where f is not equal to g and a. And there's one final problem which I just came up in describing why we want to do this with f not equal to g and a, which is also just saying that f is not equal to g doesn't really seem like a very good guarantee, especially if, like, if we're thinking of epsilon as kind of some noise level or noise threshold. If they're bounded by, if they're actually like not equal, but within this noise threshold, we wouldn't really think of them as being different up to this this noise threshold. So to fix that, whoops, there we go. Okay, what we're going to need to add is something that would be like a bounded gap that doesn't change with epsilon. So we'll say A is approximable by matrix algebras if there is some function on the algebra which is 0 if and only if A is equal to 0. And then this is the meaningful part here. Okay, so for every epsilon and every finite subset, there is an epsilon representation such that the difference between these two elements of the finite subset f is greater than delta f minus g. So if f minus g are equal in the algebra A, then there's no requirement here. This just has to be greater than or equal to 0. But if this, if f minus g are different in A, then they have to be bounded below by something which is independent of epsilon. And I should say, technical note, if the BIs can grow arbitrarily large in epsilon representations, this may not be a good definition, even with all these technical fixes we put in. Okay, any questions about this definition? It's quite a lot to take in, really. But the idea of it, I hope, is clear, which is that we just want better and better representations, so taking epsilon smaller and smaller, while keeping a finite set of elements kind of separated apart in these epsilon representations. Okay, well, looking at this definition, it's big. And when we think about the definition of what it meant to be a matrix algebra, that was the snappy definition. It was if and only if A embeds in the matrices. Residual finite dimensionality, and especially this approximable by matrix algebras, not such a snappy definition. So I think it makes sense to look at that and say, can we fix this? And we can, if we talk about the notion of a product of algebras, that's just, you take the product set. So the elements of it are just sequences of elements of your algebra's AI. Okay, then you just apply your algebra operations component-wise to that sequence. Then you can say that an algebra is RFD if and only if A embeds in a product of matrix algebras. That's a snappy definition. It's a massive algebra over here, so this isn't like a functional, it's not very easy to tell if something embeds in an arbitrary product of matrix algebras, but at least the definition is snappy, okay? And we might like to say, well, can we do the same thing for approximable by matrix algebras? So what should we put in this place of, you know, approximable by matrix algebras if and only if A embeds in what? And so we can think about, maybe it's helpful just to think about what this this RFD idea does. Okay, so why, if A is residually finite dimensional, what product does it embed in? And the idea is that we have all these homomorphisms to matrix algebras, one for every finite subset of A. So just take the product across finite subsets of A, and for each one, take the homomorphism, for each component, take the homomorphism into the matrix algebra for that finite subset. So for approximable by matrix algebras, we might like to do the same thing. We will start with the product of matrix algebras. And the idea is maybe we could choose some sequence of finite sets such that the union of all these finite sets is dense in the polynomials, just in the usual way, like for every polynomial, we can get something, a polynomial whose coefficients are all close to the polynomial of the coefficients of the polynomial we started with, right? Maybe we could look at like polynomials with rational coefficients and then just look at some kind of like increasing degree and bound, like we could make the sequence be polynomials with bounded degree and also size of numerator and denominator in the coefficients. Okay, so then for each one of these,
William, sorry.
yeah,
just a question. So then here, this index set I is basically all the set of all subsets. Is that?
Yeah, right. I kind of
why...
was hoping this would stay under the rug, but right, this could be a really large index set here, technically speaking. Yeah. But here it's not. This has just gone back to the matrices, and it's just something we kind of get easily because now we're talking about approximable, and so we can talk about just a dense subset of the algebra, and so we can take like a countable dense subset. Kind of simplifies things a little bit. So for each one of these subsets fk, we could map into m and k. The problem is we don't actually have a homomorphism into m and k. And if we try and mod out to make it a homomorphism, well, modding out a matrix algebra by like some arbitrary matrix really kind of destroys the algebra, just sets it equal to 0 most of the time. So, but what we could think about is maybe we can mod out by, like, the elements of this product are sequences. So if we take for every k, kind of, let's say we're looking at like xi, and we look at its image in m and I in the epsilon representation, sorry, let's say the 1 over k or 1 over I representation for fi, right? So that's what we do for m and I. We take the 1 over I representation of fi. So I'm saying one variable and two different variables are written on the page. It's not my my best moment there. That should be an fk. Okay, so 1 over k representation for fk. Okay, well, what happens if we plug this into the defining polynomials for a? We'll see, because we're taking 1 over k representations, that the in each component, the polynomials are bounded in the Hilbert-Schmidt norm by 1 over k. So if we look at those, if we look at this difference here, it's bounded in each component by 1 over k. So the sequence that we get actually goes to 0. That is to say, if we look at what the defining polynomials fi minus gi go to in this product here, when we plug in this epsilon representation, then we get like an element which is a sequence of elements, and the limit of that sequence of elements is 0. So what we can do is we can mod out and set sequences which go to 0 in the whole algebra, right? So we mod out by the ideal. This is actually, it's not the ideal generated by, but just the ideal of sequences where the limit of the elements in the Hilbert-Schmidt norm is 0. Okay, any questions about this? Okay, so that's great. So we have now a way of giving a snappy definition of what it means to be approximable by matrix algebras. And there's one thing that's really annoying about this, which is it's like for some sequence n1, n2, and so on, we don't really know what sequence we're supposed to plug in there. It was one thing in the RFD case where, well, we had the same problem in the RFD case. I should say it's one thing in the finite dimensional case where it's kind of like some unknown dimension n. So A is a matrix algebra if and only if it embeds in Mn for some unknown n. But it's another thing entirely when we have a sequence. So the question is, can we get rid of this dimension sequence? Maybe we could replace Mni with M infinity, which would be like matrices which are infinite size, but eventually all the entries go to 0. So then really we have, just kind of finite dimensional matrices at any given point, but we don't have to specify the dimension as long as we're talking about like a finite subset of M infinity C. And that sounds great. It sounds like it should work perfectly until we look at the right-hand side here. And we remember that the little Hilbert-Schmidt norm doesn't necessarily make sense for this M infinity because it's normalized and we don't know what to normalize by here. We can't just divide by infinity. So we need a version of this where the little Hilbert-Schmidt norm makes sense. And the idea behind this is that we can use our homomorphism from before where we embed, I'm supposed to put in what the embedding does here, but let's just walk this through. So what we do is we take MNC and embed it in MN tensor M2C. So just to walk through what happens in that case, we can think about the little Hilbert-Schmidt norm on n by n matrices as coming from the normalized trace. So call that tau n. It just takes a trace and then divides by n. And if we take the trace of the normalized trace of X tensor the identity, where identity is a 2 by 2 matrix here, okay, then we get, well, it's just the same thing as the normalized trace of XX, which we're dividing by 2, so it's just the same thing as a normalized trace. We're dividing by 2n, I should say. So what we get is just the normalized trace of X from this. So really what we get is if we take, like, let's say we start with M2, then we tensor with M2 again, and we tensor with M2 again, we get a chain of embeddings, like M2K and then M2K plus 1 and so on, where each one of these is, it's an algebra homomorphism, because it's just X goes to X tensor the identity. And also it preserves the normalized trace and hence preserves the Hilbert-Schmidt norm. So what we can do is we can think of M2 as being inside of M4, as being inside of M8, and so on. And then we can think of it as a subset where the Hilbert-Schmidt norm on M2 comes from the Hilbert-Schmidt norm on M4, which comes from the Hilbert-Schmidt norm on M8, and so on. So then we can just let R0 be the union of M2K to the C under these embeddings. And then we can actually talk about a trace and a Hilbert-Schmidt norm on this R0. And so we can say that A is approximable by matrix algebras if and only if A embeds in sequences in R0 modulo sequences which go to 0. So that gives us a snappy version of what it means to be approximable by matrix algebras. Okay, we haven't talked at all about von Neumann or C-star algebras yet, and we need to get to it. And to get to it, we need to look back at B of H. Come in with a question if you want about this stuff, but otherwise I'll keep moving. So we looked at matrix algebras which embed in MNC, and of course B of H is a nice generalization of MNC, so it makes sense to also ask what algebras embed in B of H. And from B of H, actually from matrices as well, but we don't really need it as much there, we have an operator norm. And so we can think about that as a norm on A. And it turns out this gives us a way to characterize what algebras embed in B of H. We can say there are algebras with a norm satisfying certain conditions. If you want to look at what the conditions are, you can Google pre-C-star algebra. That's what this is called. It's not a very practical criterion if you've got some infinite dimensional algebra asking, it's given in terms of like a finite presentation. You want to figure out if it has a norm. It's not usually very easy. And we can do a little better. This isn't much better, but in some situations it's easier than figuring out if an algebra has a norm like this. And we can ask whether the algebra has a state. So, and then use what's called the GNS theorem. Okay, so here's the theorem. It says a state on the algebra can be used to construct a homomorphism to B of H, which we call the GNS representation. And a state is a linear functional A to C satisfying certain conditions. Positivity, it's got to be normalized, and some boundedness conditions if we're talking about general algebras, rather than, let's say, C-star algebras. And so sometimes it's easier to construct a state on A than a norm. So this is sometimes an improvement, sometimes it's not. It's still pretty difficult. Now, we were asking when is this, when do we have an embedding into B of H? And this really doesn't help too much with that, but we do care about embedding. So there's a term we use if this representation is an embedding, then we say that the state is faithful. So a faithful state is one where we do get an embedding. And a state is tracial if it satisfies the trace property of FAB equals FBA. So we don't need a tracial state to use this GNS representation theorem, but tracial states tend to be nicer than other states, so it's nice to work with them. Now, if we're working with a subalgebra, like an algebra embedded in B of H, then we might like A to be closed under limits. And this is getting into what a C-star algebra and a von Neumann algebra is. So if the algebra is closed in the operator norm topology, then A is called a C-star algebra. It's exactly an algebra which is closed under taking limits in the operator norm. And if we have just an arbitrary algebra embedded in B of H, then, and we are kind of want to have an algebra closed under limits, then we can easily get one. We just take the closure in the operator norm topology, and we get a C-star algebra containing A. It's called the C-star enveloping algebra of A. Now, sometimes this C-star enveloping algebra is still too small. So just to see why that is quickly, imagine we had a strictly increasing chain of closed subspaces in a Hilbert space H. Let's say necessarily infinite dimensional for the sequence to go on forever. And let Pi be the orthogonal projection onto Wi. Okay, now if P is the orthogonal projection onto the union of this increasing sequence, then it's not true that the PIs approach P in the operator norm. There's always, since these are strict containment, there's always some vector which is outside the image of Pi, but in the, outside the image of Pi, but in the image of P. So, so the difference between these two always has operator norm 1. However, if we just look at what these operators do on states, then for any pair of states, the limit of Pi applied to W inner product with V will approach the VPW. And unfortunately, it is possible to have a C-star algebra where the PIs are an A for all I, but P is not an A. So if we're trying to do things with projections, which let's say we do a lot in quantum information, C-star algebras might be a little too small for us. And so we might prefer to look at what's called the von Neumann algebra, which is an algebra which contains these and other limits. Technically, we say it's closed in the weak operator topology. Pardon me. So given an algebra in B of H, we can talk about its von Neumann enveloping algebra, and it's just the closure in the weak operator topology. So we can always get one of these. And it has a nice universal property that if B is a von Neumann algebra, and we have a homomorphism from A to B, then just like you can extend a continuous map to the closure of its domain, you could extend this homomorphism to a homomorphism on the enveloping von Neumann algebra. Okay, so we get a homomorphism from this von Neumann algebra to B, which extends the homomorphism on A. And what this means is if we're thinking about embedding problems, if we're asking about embedding into von Neumann algebras, then we might as well take the von Neumann enveloping algebra of A, because whether or not A embeds into B is going to be the same as whether the closure of A embeds into B. So thinking about these ideas about von Neumann algebras, it makes sense to go back and look at the algebra we've seen so far. We saw this R0, which was this union across matrix algebras that preserve the Hilbert-Schmidt norm. So I see I am coming up on time. So I think what I'll do, we've got a few more slides to go yet before we have a natural cutoff spot. So I will go until 4:55, if that's okay. And then stop for questions. Sure. So what we get on this algebra, we said, was we could actually talk about a trace on this algebra, a normalized trace. And that turns out that trace is a state, and it's actually a faithful state, so that the GNS representation gives us an embedding of R0 in B of H. And so we can take the von Neumann algebra closure of this, the weak operator closure of this, to get the von Neumann enveloping algebra. And this is exactly what this unique hyperfinite 2-1 factor is. So it's just this algebra that we use to kind of get rid of having to think about dimensions. Now, what about this algebra we took where we took sequences in R0n and modded out by sequences which go to 0? Does this also have a faithful tracial state? And the answer is, well, there's a possible definition of such a state. Maybe we could say that tau tilde is the limit of tau applied to the sequence elements, right? So the elements of this algebra A are sequences. And so you can say that tau tilde of a sequence is the limit of tau of the sequence. The problem is this limit in general, most of the time, isn't going to exist. And in fact, it could just be unbounded. This could go to infinity. So let's try to fix this. So first of all, we better take bounded sequences. For technical reasons, we take bounded sequences in the operator norm. Okay. And when we take bounded sequences, this sequence where we take the traces of each AI, that now has a convergent subsequence. So it would be really nice, we want to take the limit of this, but it might not exist. But it has convergent subsequences. So it'd be nice if we could just choose one of those convergent subsequences as the value of the limit. And of course, well, we could have all these there could be so many different convergent subsequences. Some of them might even overlap with each other in really complicated ways. But maybe, well, we have an axiom of choice. It's very helpful for things that involve choice. Maybe that can help us to choose a convergent subsequence, and we can get a definition of a limit where the limit always exists. That seems like a fairy tale, but it turns out to be exactly true. So if we pick what's called a non-principal ultrafilter on the natural numbers, which these exist because of the axiom of choice, then we can define what's called an ultralimit. And an ultralimit has the property that if we take the ultralimit of a sequence, a bounded sequence of real numbers, then the limit always exists and is unique. So it kind of solves our kind of a calculus problem of trying to figure out if the limits exist. They always exist with ultralimits as long as the sequence is bounded. So now we can define what's called the ultrapower of R0. We take bounded sequences, modulo sequences where the ultralimit is 0. And then for this one, we can define the state the way we want to by taking tau tilde to be the ultralimit of tau AIs. So this is a sequence of real numbers. It's bounded because these sequences are bounded. And so the ultralimit will exist. Turns out this is a faithful tracial state as well. And to get the enveloping von Neumann algebra, we take this RU. So we see that A is approximable by matrix algebras if and only if A embeds in RU. So what algebras embed in RU? Well, if we embed in RU has a faithful tracial state, and it also is a von Neumann algebra, which means we might as well assume that A is also a von Neumann algebra. And so the von Neumann algebras with faithful tracial states are exactly, that's the definition of a finite von Neumann algebra. So when we say, does every separable finite von Neumann algebra embed in RU? We're just asking, are the von Neumann algebras which could reasonably embed in RU, do they actually embed in RU? Separable here, just you can just think of this as being there to make sure the von Neumann algebra doesn't get too big. Technically speaking, RU consists of sequences. It has like a bounded cardinality, so we can't make it too big. Okay. So this is so we'll cover this slide, and then this will be a good place to stop. So I mentioned this connection between synchronous algebras and approximate representations. And I left out something about the connection between perfect strategies for synchronous games and synchronous algebras. So that is, we can also say when a synchronous game has a perfect commuting operator strategy, and that's if and only if this algebra has a tracial state to begin with. Then the other thing we said was that near perfect strategies for synchronous games correspond to approximate representations. So it turns out that having a perfect quantum strategy, like a limit of finite dimensional strategies, happens if and only if the algebra has a homomorphism to RU, exactly by the argument we just outlined. It's just now we're not worrying about embeddings anymore. On the other hand, because of MIP star equals RE, there is a synchronous non-local game with a perfect CQC strategy, but no perfect CQA strategy. So that gives us a synchronous game which has a tracial state, but no homomorphisms to RU. And then by doing some kind of just standard argumentation, right? So this algebra itself isn't a von Neumann algebra necessarily, but we can take its image inside its GNS representation and close it up. We get a separable finite von Neumann algebra with no homomorphisms to RU. So we can think about the MIP star equals RE as giving kind of a strong counterexample to Kahn embedding, even in its original formulation. And I say strong here because not only do we get an algebra which doesn't embed in RU, but it actually has no homomorphisms to RU at all. So that's a good stopping point. So I guess we take questions now.
Thank you. So if there are any questions, you can raise your hand or you can just write them in the chat.
Maybe I can start with a longer one. Hi, William. So I thought you might go and say something about if what kind of strengthenings of the MIP star equals RE result would be interesting in terms of what are interesting questions from the von Neumann algebra's point of view. If there's a sense in which this algebra that you mentioned on the previous slide that follows from our result could be made more concrete or simpler, and that would have that would be an interesting statement just from the mathematical point of view.
Yeah. So are you asking about just making AG more concrete, or about making it in a simpler form?
I guess both of them. So let's say first more concrete. So how non-concrete is it right now? And would it be interesting to make it more concrete? What would you expect to learn? And then I guess once you've made it more concrete, maybe you can make it simpler. So I wasn't going to the group's direction. I was just asking about algebras. What's interesting there that might be missing?
Yes, so great question. And I think it depends on, first of all, a question which you can answer a lot better than me, which is how concrete is this synchronous non-local game? And if this is concrete, then the question is how concrete is the A1? So kind of the two separate questions there.
Right.
And if we're satisfied that AG is concrete, then the question is just how concrete is A1? And I think you're going to get different answers about this from different people. I think it's fair to say it's a matter of taste. For me, I like to see the algebra with the presentation, and how exactly it gets turned into a von Neumann algebra isn't so interesting. Presentation is a lot more interesting to work with than the von Neumann algebra. So von Neumann algebras in general, they tend to be pretty hard to describe all elements of the algebra. But if I was to argue against that, then I would say, well, at the very least, it would be better. It would be nice to have a version of this where we would know something about how much we have to mod out to get this A1 when we look at the image in the GNS representation. So especially if we could have an algebra where the tracial state was faithful, I think that would be kind of, so we could maybe ask for like a completely, a very strong description of the von Neumann algebra, but maybe that's too much to ask for because they're just hard to describe completely in general. But I think it would be fair to say that what we don't yet have is an idea of how to get a faithful tracial state on the algebra.
I think my understanding is that in our case, the presentation is fairly explicit. So the game is there, but the tracial state is less explicit. Like it's not clear what that tracial state is.
Yes, that's a very good point, right? So I think
so
that's
already even
right.
before it being faithful. Yeah.
That's right. So maybe we could say step one would be explicitly describe the tracial state, even though it's not faithful. And step two is describe the, try and find an algebra where the state actually is faithful. Yeah. So yeah, so obviously I'm not proposing solutions to those, just trying to figure out what the actual problem is. So I think if you have both of those things, then you would say you had a reasonably concrete algebra that should really satisfy anybody. Yeah. Thanks.
Are there any other questions? Okay, then since it's 2 p.m., let's stop here. Let's thank William again for the instructive talk. Thank you. And we continue at 2:15.